Hey, this is Horner. We're going to look at the AP Physics C Rotational Motion Pretest, multiple choice questions number 41 through 50. For this problem, we have a turntable, and our original angular velocity is about 8 radians per second. They say that it slows down to a stop, so we know the final is 0 radians per second, and it does that in a time of 2.5 seconds. So now we've got most information we need. First thing we're going to have to find here is the acceleration. Once we find the acceleration, then we'll be able to find the angular displacement. So let's find that angular acceleration. We know that the final rotational speed should be equal to the original rotational speed plus alpha times time. Final is 0. This is 8 plus alpha, and then our time is 2.5. So when you solve for this one, you should get an angular acceleration value of negative 3.2 radians. So this would be a radian per second squared. Now we're going to use the equation. The angle should be equal to the original speed squared. The original speed times time plus 1/2 of the angular acceleration times time squared. We're looking for this. We know that the original was 8. We do this over a period of time at 2.5 plus 1/2 times negative 3.2, and then our time again, which is 2.5, but we need to square it. In the end, when you're done, you should end up with a displacement of 10 radians in order to stop. That's number 41. Let's go ahead and take a look at the next question, which would be number 42. Number 42, it says the graphs below show the angular velocity as a function of time. In which one is the magnitude of the angular acceleration constantly decreasing? So we know it's not this one. There's the speed here is basically just rolling along at one speed. Here we're increasing speed. Here we're decreasing speed, but it says in which one of the which one is the magnitude of the angular acceleration constantly decreasing? This is angular velocity constantly decreasing. This would be an increase in angular acceleration. If we continue to look at the slope, it's getting bigger and bigger and bigger. And here, the slope is getting smaller and smaller. Remember, the slope would be equal to the angular acceleration. So angular acceleration here is equal to the change in the angular speed divided by the change in time. So we'll see that the answer here should be letter E. Number 43 says 2 cylinders are made from the same material. They roll down an inclined plane at an angle Q with the horizontal. They start from rest. They have the same mass, but the radius of cylinder B is twice the radius of cylinder A. So we've got cylinder A, and then we would have cylinder B. In what order do they reach the bottom? This one, B is the answer. A reaches the bottom first because it does have a smaller moment of inertia. The moment of inertia, this one's going to be bigger because even though they have the same mass, this one has a much larger radius. So the radius here is 2r and the radius here is r. So it takes a lot longer to get this one going. It will maintain that speed for a longer period of time, be harder to stop, but this one will be quicker on the way back down. For number 44, we have a puck that's sitting on a frictionless air hockey table, and it's spinning in a circle. It has a mass of 5 grams and it's attached to this cord. If we pull on the cord below and we shorten this radius to 1 meter, so it used to be at 2, now it's going to be at 1, they want us to find the new angular velocity in radians per second. This is an angular momentum problem, and we know that the original angular momentum should be equal to the moment of inertia of the puck times its original angular velocity, and then the final should be equal to the final moment of inertia times the final angular velocity. We can set those two things equal to each other, so I know that these two are equal to each other. And go ahead and put some numbers in. Because this is acting like a point mass, we know that the moment of inertia is mr squared times our original angular speed, and then we take it m times r final squared times the angular speed final. At this point, we notice that the masses don't matter, and we can go ahead and plug some numbers in. Our original radius was 2, and we square it. The original angular velocity is 3. The final radius is 1 squared, and then our final angular velocity is WF, is omega F. And we find out that 2 squared is 4, 4 times 3 is 12, and so it would be 12 would be equal to our final angular velocity, and that is letter C. For number 45, which is our next question, it says, I have a cylinder of mass m and radius r, whose moment of inertia about the center is 1/2 mr squared. Without slipping, it rolls without slipping along a level surface. The maximum vertical height to which it can roll if it ascends up an incline. And this one is really easy to do. So we've got it, it's going in this direction, and then it rolls up an incline like this. And so what we've got to do is do all our math to kind of figure out what's going on here. We know that the kinetic energy of translational motion plus the kinetic energy of rotational motion is what we have at the bottom, and then at the top we have potential energy due to gravity. So at this point we can go ahead and set up some equations. We're going to say that the translational kinetic plus the rotational kinetic should be equal to UG. Translational kinetic is just 1/2 mv squared plus 1/2, and this is I omega squared for rotational kinetic, and that's equal to mgh. At this point we need to go ahead and plug some things in. We know that 1/2 of mv squared is translational. This is 1/2, and then I, they told us, is 1/2 mr squared, and then omega, well remember omega times r is equal to v. So if I solve this for omega, I get v over r. So I'm going to, for this omega, I'm going to put in v squared over r squared, and that all is equal to mgh. We can now cross off the r squareds. We can cross off all of the masses, and we can rewrite what we have. It'd be 1/2 v squared plus 1/4 v squared is equal to mgh. This needs to be over 4, so it's going to be 2/4 plus 1/4 is going to give us 3/4 of v squared is equal to gh. I didn't mean for that m to be there. And it wants us to find the velocity. So our velocity here, it wants to know the maximum height. So we want to solve for h, and if we solve for h is going to be equal to 3v squared all over 4g. And that would be answer letter C. So pretty swift little problem, one that's pretty easy to solve as long as you can do your algebra. For number 46, now I've got a particle that is moving towards this circular disk. It collides and it sticks to it, so we know that this is going to be an inelastic collision. And so we know that momentum is conserved, but kinetic energy is not. Because kinetic energy is not conserved, we cannot find the final angular velocity using kinetic energy. Instead, we're going to have to use momentum. So I know the momentum before should be equal to the momentum of the system afterwards. The momentum before is mvr, and the momentum afterwards, rotationally, is I omega. Here we've got mv, let's go ahead and put an O on this one, r is equal to, and our final I is going to be the rotational inertia of the disk with this little mass on top of it. So we've got two inertias that we need to add together. So this is really the total inertia. We're going to do 1/2 of big M r squared, so that's for this disk. And then we need to add to it this little point mass, and its rotational inertia is mr squared because it's going around the outside of the disk, so kind of like a planet, times omega. Now we can solve for omega, and then we will find out what that angular velocity is. So omega is equal to mvor, and that's over 1/2 of mr squared plus mr squared. Now the m's here are a little bit different. it says we have this is little m, so we better make it a little m. This one is going to be a little m also. And so what we need to do to the top and the bottom is let's get rid of an r. So we can do that. We're going to move the 2 to the top, so we're going to have 2 times little m times VO, and that's over. Now we multiplied the bottom by 2 and the top by 2 in order to get rid of the 1/2. So this is going to be capital M R plus, and then 2 times little mr. So if we look for this one, it's not A, it's definitely not B. Here's the 2MV, but this one doesn't have any R's in it. This one has a 2MV, a little mr, and a big MR, and that's what we've got here. So our answer is letter D. For number 47, we'll go on with the next one here. It says, which arrangement of particles, all of mass m, has the smallest moment of inertia? They are all free to rotate in the plane of the page, and the axis of rotation is perpendicular to page at the point marked x. So it's rotating around the x for each one of these. So let's go ahead and think about this one. We don't need to worry about positive and negative. We're just looking at the moment of inertia of the entire system. So it's really just the sum of all the moments. This one would be 2 times 1, which would be 2. 1 times 1 is 1. 1 times 1 is also 1. So 2 plus 1 would be 4. So our total moment here is 4. For this next one, this one is going to be 2 times 2 is 4 plus 1r times 2 is going to be 6. So this is 4 on this side, and this is 2 on this side. We add them, we get 6. For this one, we've got 2 times 2, which is 4, plus 1 is 5. Oops, this is going to be 1 mass times 1 length. So that gives us 1. So the total for this one is 5. For letter D, we're starting here. We don't worry about the masses here, so we have 2 times 3, which is 6 again. And then here, this one we don't worry about. That's our pivot point, so we have 2 masses times 3, which is also 6. So now that we've seen this, the one that is the smallest moment of inertia has got to be letter A. For number 48, we have a uniform rod here, and there's a 15 Newton force that acts on the end of it. It makes it pivot about the center of mass. The rod starts from rest and attains an angular velocity of 10 radians per second in exactly 2 seconds. So what is the moment of inertia of the rod? We know that torque for this rod should be equal to the moment of inertia times the angular acceleration, and we can find the angular acceleration from the information they gave us here. So that starts at rest. So we know that we want our change in omega over change in time. If it starts at rest, that's 0. And our original speed here, or velocity, is 10 radians per second. And it moves to that speed in 2 seconds. So our angular acceleration here should be 5 radians per second squared. They told us that there is a 15 Newton force. It acts over 1 meter. So that's our torque. 15 times 1 is equal to I times alpha, which is 5. So our value for I should be equal to 3 units. And that is answer letter A. For the next one, we've got a disk which is free to rotate about the perpendicular to the disk through its center. If the disk starts from resting and accelerates to 3, should be radians per second squared. For 4 seconds. Its angular displacement along this time should be equal to 24 radians. That one is pretty easy to solve for. Basically what you do here is you just say that we've got here we go, we need to find out, it does, here's our rate, so that's our angular acceleration. So that's alpha, and it does it for 4 seconds. It starts from rest, so let's go ahead and do our equation. It is the final displacement should be equal to omega times t plus 1/2 of a t squared, and so now we're going to say this is equal to, we know the original speed is 0, so don't worry about it. We have 1/2 times alpha, which is 3, times 4 squared. 4 squared would be 16 times 3, and then we're going to divide that by 2, and we end up with 24 radians. And so your answer is letter D. And finally, the last one, this one is number 50. It says a disk is sliding on a horizontal surface that has negligible friction with a rod that is free to rotate and rotate on the surface as shown in the top view above. Which of the following quantities must be the same for the disk rod system after the collision? So the picture, of course, is not here, but you do have a disk sliding on a horizontal surface and it collides with a rod. So here we just have a disk, and there's a rod that's kind of sitting here, looks like this, and it's pivoting. So when it hits, they are allowed to kind of go around in a circle. Angular momentum, we know, is conserved in this because there are no external torques. Momentum is also conserved because there's not any internal forces. Kinetic energy could be conserved, but doesn't have to be at all. So both 1 and 2 need to be conserved, and so that letter would be C. So remember, momentum is conserved, but kinetic energy doesn't have to be, especially in this type of collision. We're not sure if it's a totally elastic or if it's an inelastic. And that is number 50, and we are done with this section.